Hello everyone, my name is Zach Prezan. I'm a PhD student at Stanford University. I'll give you a brief overview of my CMWR poster for this year. So the central problem that we're looking at with this poster is the concept of forecasting future groundwater quality. Now in the past, reactive transport models, process-based models, have been used to forecast future conditions and instances of remediation, but they've had largely mixed performance. And so instead, we're actually looking at what data-driven models can be used to forecast future groundwater quality. And specifically, we're looking at three different types of data-driven models. Now, if I zoom in here, I'm just going to briefly go over the actual data set that we're using. So this is all synthetically generated data from a reactive transport model from CrunchFlow. And it's a model designed to simulate variable redox conditions within a fully saturated floodplain. And so specifically, we're looking at concentrations of iron 2 because they're a good indicator of redox conditions within groundwater. But you could imagine these results could extend to any type of redox sensitive nutrient or contaminant or metal. And so we have this 2 meter by 15 meter domain with two different types of sediment. We apply annual forcing to it, designed to simulate seasonal floods. And then out of that, we get 10 years of iron 2 concentrations, or actually more than just iron 2, other species as well, at several different points within the domain. And so each of those time series we then take and subsample to weekly samples, because that's something that's somewhat reasonable to collect in the actual field. But then to simulate sort of the randomness and the unfortunate experiences that many of us have had sampling groundwater in the field, we randomly mask out about 20% of samples because vials break or maybe you can't get to the site, etc., to try to generate a time series with inconsistent observations and missing values, just like we observe in real life. And so we take each of these time series and then apply three different types of models to them to try to forecast future conditions. The first is ARIMA. Second is a long short-term memory network, a type of recurrent neural network. And the third is a variant of an LSTM, a time-aware LSTM, which is very similar for those who are familiar with long short-term memory networks and the architecture of an LSTM. A TLSTM or time-aware LSTM is very similar, except it adds a single gate that discounts previous values or previous observations based on the time that has elapsed since the previous observation. If you have more questions, I direct you to the reference that we have listed in here. They give a really great overview. And so for each of these, we have 20 total time series. Each time series is 10 years long, and we train on the first 8 years and then test on the final 2 years. And you can see in this table here, we have three different weighted RMSEs. Yet you can see that the error on the TLSTM is clearly the best. It's 2 orders of magnitude lower than the LSTM and an order of magnitude lower than ARIMA. And if I pick out just one individual time series and try to look at where the differences are most pronounced, and these three types of models really distinguish themselves when you're trying to forecast following a period with a lot of missing observations. And so in each of these plots, the blue is the ground truth, the black points are the points that we've subsampled from there with missing values, and then these blue crosses, those are the actual forecasted future values. And so ARIMA and LSTM, they really don't do all that well going forward and rolling themselves forward over periods longer than a month or so. Whereas the TLSTM, it's able to forecast a little bit longer into the future. And even though the start of this forecasting period begins, where the concentrations of iron 2 are decreasing, it recognizes that 6 to 7 months in the future, conditions will rebound. And sure, we overshoot that little dip, the minimum in that year, but nonetheless, the TLSTM still performs pretty well. And so I think this is an interesting start and intriguing, many intriguing options for future work. And so I'd encourage you to finish reading the poster, or in the session on Monday, please reach out to me. I'd be happy to discuss it more. Thanks.